Well, welcome everybody. My name is Subir Sachdev. I'm chair of the physics department, and it's a pleasure to welcome you to the David M. Lee Historical Lecture in Physics and the presentation of the Maurice Goldhaber Prize in Physics awarded to outstanding graduate students. After the lecture, you're welcome to join us upstairs on the fourth floor of Jefferson 450 in the library for a small reception with desserts and soft drinks. Please remember to take all of your belongings with you because we will not be returning to this room. Okay, so now it's my pleasure to award the Maurice Goldhaber Prize, which is awarded annually to outstanding graduate students in the department. Usually the prize is awarded to one outstanding experimental graduate student and one outstanding theoretical graduate students. But this year there were so many excellent candidates that the faculty decided to award 3 prizes, with the third prize going to a student who works both in theory and in experiment. Okay, so the winners of this year's Maurice Goldhaber Prizes are Victor Buza, the prize for the experimental graduate student is Alexander Kiesling. And the third prize is for Alexandra Thompson, who's not here. She's actually my student, and she happens to be in India attending the wedding of one of my other students. So, and, yes. And she did tell me that she was doing this. Okay. I would also like to recognize Ana Maria Laclaru, winner of the Harvard Merit Award, awarded by the Faculty Arts of Sciences. So, Ana Maria, I don't have anything to offer you, but I guess you can come here and we can shake hands or something. Congratulations. So now I turn the podium over to Professor Erwin Shapiro, who will introduce our guest speaker, Professor Rainer Weiss.
Thank you. Thank you, Sabir. It's a true pleasure for me to introduce Ray Weiss this evening. When I told him I was going to introduce him, he had one thing to tell me. He said, make it short, just say, here's Ray, and be done with it and sit down. And I've known Ray for now close to half a century. And I know very well that when he says something, he means it, and when he means something, he says it. But I can't quite do that. So I'll be relatively short, and I hope you will forgive me. This whole question of observing gravitational waves started with Joe Weber in the 1960s, reaching a climax of sorts in the late 1960s and early 70s, where he was a little over-exuberant and felt he had discovered gravitational waves when he had discovered nothing but noise, as a close examination of his data illustrated. But it got Ray thinking, and he was asked to give a course in gravitational radiation, and I think as a result of that, he decided to think for himself what he could do or what would be a good approach to observing gravitational waves. I think it was in that context that he came up with the laser interferometer approach. It's true? I'm telling the truth? Wow. Yeah, and you were asked to give it. Yeah. Anyway, so the rest is sort of history. And I will be very short now and just say that in his way to achieving, where he was the central character, I think it's fair to say, although he might dispute it, but only slightly, in the ultimate detection of gravitational waves, he made plenty of waves on the way to discovering the gravitational waves a couple of years ago. And with that, I'll turn the floor over to Ray.
You did good. You did good. Thank you. I got a mic. All right, let's see if I can make this work. Can you guys hear me in the back? Yep. Can you really? Okay. Because I'm not going to talk about science, so the words are important. I'm going to talk about what that title says, which is this remarkable thing that the NSF did to support this. And I'm doing this for many, many reasons. First of all, as you'll see as I go along, I want to honor some people who were absolutely essential to have this thing, which had a complicated, bumpy history, which I'm going to try to explain to you, that kept it going in the NSF, and that's part of it. The other thing is I'm sort of bemoaning when you get done with this, that I don't think what happened to us in LIGO is something that's so easy to happen anymore. And that worries me a great deal. That's a political statement that hasn't got to do with Trump. It has to do with the way things are reviewed in the NSF. It's way before Trump. So let me start by doing a little history. And this is the outline of what I'm going to say. And let me just see if it doesn't work to have, can you see this? Yep. Oh, wonderful. I don't have to point then. Okay, is that really, you can see the, whoops, you can see the cursor? Yep. All right, good. Well, so anyway, I'll talk about the beginnings. No, leave it right there. And then I'll talk about how, I'm going to go through what is up there. I mean, these are all human stories. How did Caltech and MIT get together, which is an important part. And then some very difficult things. The transition from tabletop physics to something big, which is not easy, especially for people who are inventive and want to do things on their own. And then I want to show you how the NSF particularly got to the point where they were willing to go along with this. And I'll get to that, and that's an important part of this all. And then the two committees that looked at us, and then really at the end, what the project, which was, and people have to look at why was it that Barry Barish, who was not in this field, was part of the Nobel Prize. He had a very good reason for being, and that's what that last bottom real project and some good things we did is all due to Barry. So let me start with something this is complicated, and I'll just say it in words first, is that when Einstein developed general relativity in 2015, he didn't have gravitational waves in it. He had the field equations. And then 2016, he wrote a perturbation calculation. It's not 1916. Oh, my God. Oi. All right. Sorry, 1916. Both of those 19s, okay? He actually did a perturbation calculation, linearized equations, and saw that there were various things that he had predicted already. The perihelion advance was already easy to do that way, or easier to do. And also the fact that there were gravitational waves was something that had been in his mind. And he does it wrong in that 1916 paper. He shows the kinematics for the waves, right? He says they go at the velocity of light. And he also shows what they do. He shows that they do stretching of space in one dimension that's perpendicular to the wave. It's a transverse wave, stretches space in one dimension, while correspondingly contracting space in the other. So there's a push-pull strain pattern that looks quadrupolar, and that travels along at the velocity of light. He did that right. He even got the equation which is above, and I'll point it to here. This equation, well, let me see where I find it. There it is. This complicated looking equation, we'll get to that if we want to. It tells you what it's the Poynting equation for gravitational waves. And what it says is the strain, that's the derivative of the strain. That's the delta L divided by L. And that's what H is. It's that strain in the wave, which is a characteristic property. Comes in two polarizations. Let's not worry about it. But shows how the strain, whoops, maybe I do have to use the pointer because I lose it. This terrible factor here, that's huge number, this is the power per area. That's the intensity. A little bit of H doesn't do much. You have to got a huge H with a big second derivative, first derivative squared, to get any value of the power. And so that turns out that this thing tells you it's going to be difficult. But I want you to go over here with me to talk about this, because this relates to the statement that Einstein made at the end of that paper. The thing he had wrong in that paper, by the way, and if you're interested in the history of it, you'll see he predicted that monopole radiation exists in gravitational waves. That's completely nutty. But he made a mistake, a physics mistake. And he showed in the formula the relationship between the distribution of the accelerations in the sources. This acceleration is the same. It's the source of the gravitational waves. And he showed in that paper that something which is uniformly accelerated, spherically symmetrically accelerated, would radiate gravitational waves. He gets the orders of magnitude right for everything, and that's what this is all about. At the end of the paper, he says, this equation, which is up on top here, does this pointer disappear? Is that what happens? Yeah. Ah, that's the trouble. Okay. No. All right, so I have to move it around. Well, let me do it this way. That equation way up there, that's the intensity in the wave, and that's a property of the source, namely the derivatives of the moments of inertia and so forth. And there's a constant in front. And he bemoans here that that constant is going to be tiny. And in fact, makes this statement. In German, he says it here, but I have it in English for you. In any case, one can think of A, that quantity, will have a practically vanishing value. And now I have asked the people, he says that statement outright, this is never going to amount to a hill of peas. And the thing is that you must try to figure out what he was doing. And I tried to do that as sort of presumptive and make believe I'm Einstein for that line, the next line down, which is, let's look at the formula, which is actually, this is the formula for H from simple reasoning. And let's look at here. That's H, that's the strain, the field quantity of gravitational waves. And the first factor is gm over rc squared. In other words, that's the Newtonian constant. That's the mass of the system. That's the distance you're away from it. And c squared is the velocity of light squared. That quantity is a measure of how strong gravity is. And so consequently, for example, just so you have a feeling for it, you and I are living in that, where that's about 10 to the minus 10, small. On the sun, at the surface of the sun, where it's about 10 to the minus 6. And on an event horizon of a black hole, it's about 1. And so you can then, and the v squared over c squared is just a way of saying how much energy really effectively, or how much motion is there in the system. And that's the velocity in the system. And so it's non-spherical motion we're talking about. For example, two objects going around each other in an orbit, they will radiate. Two objects that are coming at each other will radiate. But a thing that's uniformly expanding and contracting will not radiate. And that's the mistake he made. He corrects that in 1918 and actually gets the quadrupole formula, but to a factor of 2. And by the way, it's a very interesting insight into Einstein in the 1918 paper. He admits that there was something wrong in that 1916 paper, but it says he attributes it to an arithmetic error. That's not true. It was really a physics error or a mathematics error. And even when he gets a quadrupole formula, he makes a real arithmetic error. There's a factor of 2, which he just left out. So anyway, let me give you one example. For example, let's suppose take two trains that are hitting each other. And that's something he could have had in his day, and those trains were moving about as fast then as they are now, which is a tragedy, I have to tell you that. So you do 100 kilograms for the mass. You can plug these numbers in, 100 kilometers per hour for the velocity, collision time of 1/3 of a second, so that you have to know how far away you are. You can't just do this right where the locomotives are colliding, because you'll see the near field. You have to go out far enough away so you're in the radiation field. And that you need some time like that. So you go 300 kilometers away, and you wind up with an H value that's 10 to the minus 42. That is truly too small. Nobody can make that measurement now. Okay? So yeah, I can see why he might have made that statement. Well, look, by the way, I've asked the Einstein people to look for the back of an envelope calculations that he did, and they haven't found them anywhere, or a notebook and where he had done this. The other one is a better example, and that's an example where you take a thing where you look through a telescope, and you look at a binary star, which certainly they knew about. They didn't have the dimensions of the galaxy right, but let's take again. We'll put in two masses, about a solar mass each for those guys, an orbit of a day. Let's say they're 10 light years away, which is something I have to guess at. I don't know what Einstein would have put in here, because he didn't know about the galaxy. And then you say you get a number for H about 10 to the minus 23 with a period of half a day. That's not nutty, that number, although it's kind of small. We think we nowadays can measure things like that, but not in those days. That was hopeless. And so one way, if you want to say, could he have seen something, you say, what's the Q of that system? How long would that system have died? How long would it have taken for that system to die, to get close to each other? And you get a number like 10 to the 15 years. I think that's 10 to the 13 years. Clearly not something within the lifetime of an astronomer. So this is even on the astronomical setting, what they knew about, they couldn't do this. And so a lot of things have changed since then. I'm not going to go into that. This is not a science colloquium. That's a people colloquium, and we'll get to that in a minute. But the thing is that the reason why things changed is because the technology got better, hugely better. And the other thing is because the people began to realize that there was much more in astronomy than those kind of binaries. In fact, that's what we detected, and I'll talk a little at the end about that. The black holes and the neutron stars are just these very, very dense objects that are very close together with very high frequencies compared to anything like this. And though all these things contribute to your ability to measure. Okay, so that's, okay, we'll get to that. So now, as was mentioned in the introduction by Erwin, here's Joe, and I'll give you a little history of that. What had happened is, I don't know how many of you are aware of the 1957 conference in North Carolina, the Chapel Hill Conference on new thinking in gravity. It was a remarkable conference. It's well worth reading if you're a historian, or even if you're just a physicist. Because they have a very good notes of that meeting, and the Max Planck Society has put out a volume on it. And you'll see Feynman was there, and Feynman kept saying, look, tell me what you can do as an experiment. Tell me what you can do as an experiment. The hell with all this theory. And that was the way he was approaching it. And he says, enough of the theory, all right? What can you do to show any of this? And this was the problem. For example, MIT, you mentioned that I taught a course at MIT. Well, it turns out there was courses taught at MIT in the 1920s on relativity in the physics department, general relativity. And then when nothing looked like ever was going to happen, I mean, the cosmology and all these tests of relativity, which were much, you did one of probably the last, the test that, new test, the fourth test, you did it at a time which was what, in the 60s, right? Yeah. So in other words, all that time, from the 20s to 40 years of not much progress in anything experimental. And that put the thing into the math department. And when I got to MIT later on, it was taught in the math department. It was taught as differential geometry. That's what it was taught as, part of math. And by the time I taught this, which was about 66 or 67, I've forgotten exactly the year, there was suddenly interest in MIT again, because things had changed. Technology had changed, and because of that Chapel Hill Conference. And at the Chapel Hill Conference was the idea that, and this is an idea that both Joe Weber had and John Wheeler had together. Let's try to make a reality out of gravitational waves. And the idea they had, and there was Joe himself has most of it, but Wheeler was much behind this, was the idea of a bar. This is the big aluminum bar. You can see there's Joe Weber. And the idea was that the stresses in that bar, which were quadrupolar stresses, stretching and compression, would excite that bar. Some Fourier component would excite that bar coming in from the gravitational waves coming in from the outside, would excite that bar at the ring, and as it went through, it left it ringing. And that was the idea, and you had strain gauges, which he, in fact, is mounting right there to that thing, so to pick up that vibration. And there's the vacuum system it goes into. And so Joe, people began to realize he was doing this experiment by about 1963 or so. And as Erwin told you, by 69, he wrote a paper, which was very extremely influential, which was said, evidence for the discovery of gravitational waves. He was a little cautious, but not as cautious as he should have been. And what happened is that started, and this is now the beginning of the human story, okay? The part that made why I say it's so admirable that the NSF got into this. What happened was that many people immediately went to this because it was not such a hard experiment. Look at that. It's not so terribly hard to instrument a bar like that. Some people did it better than Joe. One of the people who did it better than him was Dick Garwin. Dick Garwin, who was at the IBM labs, at Watson Labs in New York at the time. He's a superb experimenter, one of Fermi's last students, if I remember right. And he did a little bar, but he instrumented it properly. He knew everything about it. Joe built this big thing and didn't quite have it all right. It turns out if he had thought about it a little more, he would have put little weights at the ends of the bar and put the strain gauges between the weights. He wouldn't have put in the middle. He would have, because the motion isn't very big in the middle. The motion is big at the ends of the bar. So, in a free bar like that. So he would have done better with that. He would have done better with amplifiers that he didn't have at the time. So it turns out Dick Garwin did it all right, but he built a little one. And so what happened is, and this is a very serious piece of this whole story, which will come back again when we talk about LIGO. What happened is that Garwin would confront Weber, and were you at some of those meetings? I bet you were. And I'm going to tell the whole story, right? I'm going to tell a little of the story. The meetings were kind of awful. What happened is Joe would talk about his discoveries and his pulses he was seeing typically after he'd done the following. He'd put one bar in in his lab at Maryland, another one on a golf course about 8 miles away, and another one about 800 miles away in Chicago. That was the basic idea, and he was seeing coincident events in these, sort of 2 or 3 a day. And that was something he would show people the data, and they show how it slowly filled in. And it looked like he wasn't seeing the center of the galaxy for a while, but then all of a sudden he was, because Neyman showed him that maybe he should have the center of the galaxy in there. That's one of the hypotheses. But nevertheless, there was plenty of things about the data, but the big thing was this. Everybody else who had been working on this, and especially Dick Garwin, did not see anything. And there was a very good German group we'll see in a minute, but the important person in this thing was Garwin, because Garwin just took him on. And the thing that was sort of really quite awful was to watch Weber defend himself against Garwin. And what happened is that Garwin would just say, I see nothing here, here's the sensitivity, I know exactly how so much a smaller thing I can measure, and and Weber's only response to Garwin was, you didn't do it my way. And that is not a response, not in science. I mean, he did not have all the data that Garwin had on the instrument. And so it turned out that in the end, the whole field went down with this. In other words, Garwin was convinced that this was pathological science and that this was science that was never going to go anywhere. So, okay. And that sort of, the reason why I bring that up and make a big fuss about it, that is the mindset that was in the scientific community when this whole thing started with interferometry as well. And so it turns out the idea of interferometers, well, okay. Now it was something that came up in many places, all unknown to everybody else. It turns out the Russians first had the idea. A guy named Gerstenstein Pusovit had the idea in 1962. None of us knew about it. 62. And they put out a little paper saying, look, if you want to detect gravitational waves, you could do it with large structures in space and big spaces, big distances. And but they didn't do any calculations for the noise. They just said, look, there's a better way of doing this than Weber bars. Then Weber himself, in one of his notebooks, says, look, maybe if you want to make a better sensor for one of these bars, use an interferometer. And then Bob Forward, who we were just talking about, had the same idea. Bob Forward was a student of Weber's, and he started building some interferometers, but mostly with the intent in mind of being a better readout for a bar. And I was in RLE at the time, and I thought of it really much more like the way the Russians did, and I didn't know anything about the Russians. So, okay, then I developed the whole thing, and I ran into, and this is now the first piece of history, I was asked to run a committee by Nancy Roman at NASA headquarters in 1975 to see what could the space program do for cosmology and gravitation. It was a committee, and I don't know if you can read, but it's there. It's hard for me to read it. But this is the program of the different topics that committee in a report actually did. And in there, you'll see, for example, tests of the principle of equivalence, gravitational radiation, cosmology and gravitation, all these topics. What could the space program do in it? And the members of the committee were well, okay, I have Irwin not as a member, but as a guy who gave us testimony, which is, you gave us testimony to that committee. You may not remember that. You don't remember. Okay, but I'll tell you, let me tell you who was on the committee. Peter Bender, who is now a guy who's in Agila, actually is the guy who is most responsible for LISA, which is another technique for doing gravitational wave radiation using the space program. But he didn't know that when he came to the committee. We invented LISA on that committee, okay? Robert Pound, who's from here, who had just done the redshift with the Mossbauer experiment, okay? And the theorist was Charlie Misner. And Charlie Misner, I asked Kip Thorne to be on the committee, but he was too busy. And that was it. So Kip also came to talk to the committee. He was, you and Kip, and I think that was it, were the people who were not on the committee but gave testimony. And you gave testimony about solar system tests, and so did Kip, about the whole PPN expansion. That's what he mostly was working on at the time. And then Kip and I, this is where the collaboration between Caltech and MIT started. And but let me show you, I'm just getting ahead of my story. Here's Kip, just so you know what he looks like. He was a young man at that time. We all look different now. But Kip had written a book with Charlie and Wheeler together, and with Misner. And in that book is a very interesting little thing. I will only tell you what's on there. These pictures that you can see better than I can are different in the book. Kip wrote the part of the book that has to do with different kinds of gravitational wave detectors. And in there is all the different kinds that people had thought of. He had even invented some himself, but all based on the idea of a mechanical system that has to be driven and has springs in it and in fact, variance on the Weber bar. That's what that was. And he had a project. A very top one is the one he rejects, the idea that you send light between two places. He says that one will never be sensitive enough. And he gives it as a problem in his book. If you can find it, since you own the book, you can probably find it. It's this problem right there. And he makes this statement up here, which I can only read from my own computer, but you can read it. It says that laser interferometers, several features of such detectors are explored in exercise 37.6, 37.7, which are up there. As shown in exercise 37.7, such detectors have so low a sensitivity they have of little experimental interest, okay? So, the hell with laser interferometers, they won't work. And what did he do wrong? I can tell you exactly what he did wrong. And what happened is, I didn't know that at the time, and we'll get back to Kip in a minute. But what he forgot about is that you can have more than one photon. That's fundamentally the mistake he made. More than one photon. And that little calculation is done on the side here. Here's the H value you can get if you talk about sort of like what comes out of a laser. 10 to the 23 photons, and then you can finally kind of break a fringe up into 10 to the 11, 10 to the 12 parts, and that's what you need to do. Okay, so let's get back to Kip, and I want to get back to Kip, and then I'll talk to you about this picture. What happened is Kip and I hardly knew him, and he looked like a guy that he didn't have a hotel at the time when he came to talk to our committee, and we had to spend the night together. Not in one bed, don't worry about it. But the thing was that what we did was we spent pretty much all night talking about a project that he was interested in. And the project was, he had this first-class group of theorists at Caltech. Bill Press was one of them. Saul Tukolsky was another. I mean, some of the real heroes of this relativity field, of our current field, were students in Kip's lab, in Kip's group. And he had the idea that it would be better for Caltech not just to have a theoretical group. He wanted to say, what should Caltech get into as an experiment? And he wanted to use whatever this committee was thinking about and what I was thinking about as a way of sort of at least giving some new ideas, maybe ideas he hadn't thought of yet. And so we talked about a panoply of all the things that list of topics that were the topics of that committee. And sort of in the middle of it all, we came to the point of gravitational waves. So I don't know, maybe 3 in the morning. And what happened is that he hadn't really thought through. That book, I'd never read the book up to that. Well, the book predates this. I hadn't read that. But he was still thinking that way. And so within about 15 minutes, he was convinced, after he listened to what I told him, that using interferometry for gravitational waves, if you make them big enough, was the way for Caltech and him to go. Okay? That was amazing. I watched this. And so he asked me, who in the world is working on this? And that's behind me are the people who were working on it at the time. And so, here is the group at MIT, a very small group of grad students at the time, and there were some ideas and then a prototype that I had built. The group that really was first class, not the MIT group, was not first class. It was these people who this is the head of the group, who was working with a Weber bar. These were the German group in Munich who had actually, as far as I'm concerned, really shown that Weber was wrong. Because they had done a very careful job. They understood their noise. They understood everything about their instrument, even better than Dick Garwin. And what happened is I had put a proposal into the NSF. They were asked to review it, and the Europeans didn't know quite the etiquette for doing that. Heinz Billings calls me up and says, I see your proposal. Do you have anybody who've graduated? And I was very surprised, because you're not supposed to know that. And I said, no, we haven't gotten that far yet. We have starting. We have a few people, but nobody's graduated. Well, I'd like to, would you mind if we also get into this field? I said, no, how can you mind? And so they have a very good group of engineers and people working. And Frau Schnupp especially was a lady who had a lot of clever ideas, and so did Rüdiger and Schilling, and these were younger people at the time. And they had very quickly built a 3-meter prototype, based a little bit on my proposal, but not only on it. And they had shown that they were getting better than a bar. They were doing better in sensitivity than a bar. And then with that knowledge, they went on and built a 30-meter system. They just want to show does a scaling law work, and it did. Okay, that's very important in this story. So they were the first to show that the calculations that were made and the calculations you do make once you understand the system a little bit do pretty much describe the way such a system operates. At the same time, there was a group in Glasgow. This is Ron Drever, who later moved to Caltech, and people in his group. Brian Mears, for example, was a young postdoc at the time who invented a very clever idea, how to make the interferometer spectral response change. But all of these people played a big role. And so I suggested to Kip, look, if you want to get into this business, why don't you go to these groups and hire some of the younger people, one or two of them? Well, okay, he looked at that, and he found that he couldn't hire the people in the German group because they were all engineers, and they would not be credible with his faculty, which was unfortunate. And so then he looked at the Scots group, and he hired Ron Drever, which was a wise decision, but none of us knew how complicated Ron was. Okay, and that will come back and plague us through the rest of this. He was a very intelligent, extremely creative man, but a very complicated man to work with. And that then showed up later, okay? And so anyway, so there is this group. Okay, that's the group of people who were working in the interferometer business in the sort of mid-70s when Caltech made this decision. Now, here comes the other side. This is now the side from the NSF. This person is Richard Isaacson, and he was a student of Misner's, and he had taught at Illinois University, not Illinois, but Illinois Tech, which is in Chicago, but he didn't like teaching. And so he got a job at the NSF in about 1974. And he became the discipline chief for gravity, which is, you must have got support from him at the time also. And what happened is he's the one who got my proposal and sent it all over the world, which is fine. But he also is now the guy who did something really quite remarkable. What he did is he himself had written a very interesting paper, which is that paper up here. And I will only tell you what's in it. It's underlined. I can't read it from here. But he did something which at that time was still not well understood. Namely, Eddington had run into the trouble himself. When he wrote his own book on relativity back in the 20s, he found out that if he applied the weak field equations that Einstein had put into the 1916 paper, and he tried it and it really did the calculation, he found out that binary star systems didn't lose energy to gravitational waves. They made energy somehow from nowhere. Okay, they got more and more energy. And so he said the whole thing is nuts. And he wrote a very famous statement, gravitational waves move at the speed of thought. And there's a book out about this. Kennefic wrote a book on the history of the gravitational waves, and that sort of sticks in your mind because he just decided to poo-poo the whole thing. And then Einstein had misgivings again in 1936, where he made a mistake with Rosen. And they made a mistake. I won't go into all of that. It's a cute story. You asked me about it at the end. I don't have the time right now. But what came out of that story is at the end, they had made a mistake. Robertson at Caltech had found the mistake. And I may as well say this much. And Einstein got irate about this, that his paper had been reviewed. That was a whole thing in the physics today about this. And that I didn't send you a paper to be reviewed. I asked it to be published. You know, that kind of thing. And so... but anyway, so what happened is that they got Robertson's mistake. They were doing gravitational wave. We're trying to find a source-free solution for gravitational waves in cylindrical coordinates. And it's a bad set of coordinates to do it in. And many of you who have fought with Einstein's relativity theory know coordinates are a terrible problem. I mean, that's a huge problem. Got Einstein in trouble a lot. Got everybody who works in the thing in trouble, even Irwin at one time in the early days of your experiment. Because you believe the coordinates. I remember you had to find invariants for each of the things you were measuring. So what happened was that the Einstein didn't believe in it either for a while. And anyway, so in general, the whole thing was sort of a flaky field. Let's put it that way. Okay. And so the guy who did one very important, solid piece of work in that, there are others, but this was a very important piece that Richard Isaacson did. He showed with a very rigorous mathematics that if you took a system and it had curvature, which means it had curvature and it was dynamic, it was moving, it would lose energy. And the way he found out that way, he just kept measuring the curvature at the source. That meant the curvature of space at that source gives you a measure of the mass, and the mass goes down if you wait, and that mass shows up at infinity. That was the calculation he did, and that's fundamentally what that paper was about. So he showed, yes, gravitational waves get generated by the accelerations, they make curvature, and that curvature eventually winds up at infinity, and that's how there's no question that there's energy carried by these things. So that was fundamental. And Rich had this in his mind, but he also had a great deal of instinct about how you popularize science and also how you manipulate science, in the sense that if you're in a place where you're responsible for funding science, he knew how to do it. And I'll give you now examples in the rest of my talk about all the things that happened along the way of the NSF, how the NSF pushed this thing through. By the way, he had a hobby, which is and it's now a profession. His hobby is the sort of the anthropology of textiles. And he had a beautiful exhibit at the Textile Museum in Washington on rugs, and that's a tent band around a yurt. And he learned a lot about tent bands and yurts, finding out that the whole history of family is written in that tent band. Sort of quite interesting stuff. Anyway, and the person he influenced first is Marcel Barden on that gravitational radiation is a good thing to work on. And what happened is that Marcel was the head of physics. He was a nuclear physicist at Columbia, had taken the job of discipline chief for physics. And Marcel got so interested in this thing that he even convinced his son to try to go into this field. He came to my lab many years later and wanted to work in this field. Marcel was, and what were they so convinced of? What they were convinced of is what you'll see these committees recommended. Let me not take it away from them. The next thing in the story, we'll get to that, is the fact that based on the success of the German system, the fact that Caltech was now going to try to go into the system as well, MIT was not the least bit interested in this at the time. In fact, they thought it was crazy. In fact, I won't go into that, but there was no real support at MIT. They were not going to support this. And the reasons were straightforward. I mean, now looking back and looking at the way administrators sometimes operate, I can understand it. Here's a flake who lives in building 20. That's me, okay? A wretched old building that never really made much noise, pushing suddenly for a $100 or $200 million project. What the hell does he know about this? That's number one, okay? Second of all, the technology wasn't quite ready yet. You had to develop it. And third, there wasn't any clear way to say, here are the sources that you're going to see and how strong they are. So it was built on a cobweb of hopes. And I can see a rigorous guy worrying about the prestige of MIT, deciding, okay, this guy's a nut. Let's not do anything for him. And that's what happened. But that all changed later, okay? Ken was a victim of that a little bit, as you know.
And Francis Lowe is the person making those decisions.
Yes, you're right.
And he was the provost and he was a physicist.
Well, they're both, well, since you're mentioning names, it was Francis because he was a physicist and John Deutsch because he was a chemist. And they were both high up in the administration and they had no use for this. Okay. So what was done was that we did a study at MIT of the following. Based on the success of partly our experiments, but mostly the German experiment, we decided, let's find out, and now this is a thing that was discussed heavily with Rich Isaacson. Should we do this? Because it's going to cost the NSF about $300,000 in 1978 dollars. That we wanted to go with industry and find out whether we could actually build a thing like a LIGO that was 4 kilometers big. Were there sites? Were the lasers adequate? Was the engineering for the vacuum systems good enough? Could you actually do it? And what would be an order of magnitude price for it? And our job was, and this is where Rich was very important, he encouraged us, don't come up with a design. Come up with scaling laws so we can play with it, okay? Which is a very, very reasonable thing. Imagine a theorist telling you something so intelligent. So what comes along as we write this up with 1983. In the meantime, Ron Drever has come to Caltech, and he comes into this kicking and screaming. He wants no part of it because he wants to do his own thing. And Kip and I had a terrible time because we had already decided that if this field is going to get done, Caltech and MIT would do it together. MIT couldn't do it alone. It had people who were not friendly to it. Top of that, Caltech had a lot of experience in this, and it had JPL. Maybe we could use JPL, stuff like that. So the idea was that there would be a collaboration between. That was decided way before this. And so Kip, in fact, one of the people who joined that study was Stan Whitcomb, who is a Caltech physicist, a very good one. And okay, that's Stan right there. And that's Peter Salson, who happened to be at MIT, was a product of Princeton. They and all of us did this study. And what came of it is, this is again the outline of the study. I will only tell you, you may not be able to read it, but what it is really, it's based into what's the experience with the prototypes, what's the noise sources are, site surveys, how do you make a construction, and then a cost estimate. And looking at how you make the ground noise isolation systems, all the different things that you need to do. And so then comes the next big event. In 1983, we go and present this to a committee of the NSF on large projects. Now, this had been completely orchestrated by Richard Isaacson and by Marcel Barton. In other words, the committee had some people on it who've been planted. Had you heard of such a thing before? I'm sure you have. But that's what it was, and I'll show you the plants. What we discussed at that meeting were all the big projects. The big one was an improvement of the Cornell synchrotron. That got the big bucks. Then LIGO was second. It got a very interesting recommendation I'll let you read in a minute. And then the last one was an improvement of you may know this, Lee, a big improvement on an Illinois synchrotron for nuclear physics. And Bob Eisenstein was, in fact, in charge of that at the time. So we got this. And I mean, here's the committee. And you can see the committee. I mean, here, for example, is the guy who one of the plants. I know this for a fact because Stan told me that. Stan Desser told me that, yeah, like Marcel called him up. He says, you come here, you got to be on that committee. Okay? And he knew why he was being asked to come. So anyway, but the committee was extremely friendly. And here's what they wrote, and here's what it is in English. And I think I'm going to read it to you because it's really quite cute. It says, the committee is impressed with the long-range scientific potential of gravitational wave detection. It will not only test our basic understanding of gravitation, but provide an entirely new window on the universe. We have considered the major interferometric laser detection system now being developed by the Caltech and MIT groups. We note that only is this an outstanding scientific opportunity, but the foundation is the only source of support for ground-based gravitational physics. And here comes the powerful sentence. As with any attempt at a qualitative advance, there are risks. Here, the uncertainties involve both the magnitude of the signals to be detected and the large extrapolation of known experimental technique inherent in the proposed scale. We find, however, the fundamental scientific merits of such an investigation so important as to be worth a substantial investment. Now, you will never get another recommendation like that. Absolutely unbelievable. Stan wrote that. Okay. Stan Desser, along with a couple of others, but he was the linchpin. So, all right. Collusion, you want to call it? What do you want to call it? I don't know what. All right? No, we had nothing to do with the Russians. No. Okay, so now, next big event. Now, what happens between then and this next big event, which is in 1986. Remember, that's now 3 years, 83. The next big event is that Dick Garwin gets wind of this. And Dick Garwin smells a rat. And he smells a rat, but in a funny way. I talked with Dick about it. And Dick said, no, he was trying to help. And he might, it's both things together. You have to read what he wrote. But the thing is, so I don't fault him. But what he demanded is this. And before I tell you about that, let me tell you what ensued between 83 and 86. What ensued between 83 and 86 was Caltech and MIT trying to make a project out of it. From people who are both quite good at tabletop things, all of a sudden to pull these disparate groups together as experimenters and try to divide the problem up into such that different parts of the problem could be done by some at Caltech, some at MIT. And it turns out that was almost impossible to do. And here I blame Ron because he just could not let go. He had to be in charge of all of it or none of it. This is one of the problems. And so what happened, we tried all sorts of ruses, and Kip almost got a heart attack out of this whole business because he had to deal with these two guys who were all the time at each other. This was Ron and me. I couldn't let Ron run everything because I knew he would do it crazy. And he wouldn't let me because he looked like I was going to dominate and take it over. He had it all wrong. But later on, I learned what was wrong with him. That's a long story. None of us really knew that he was a brilliant guy, but he had Asperger's syndrome all his life. And in fact, what happened is that he had personality problems like this, and which were such that he could not ever he didn't realize what he was doing most of the time. He was brilliant about ideas, but you argue with him about the ideas, what happened, every idea was a golden chocolate. That's the way he thought about it. And the golden chocolate sometimes was not good, sometimes it was good. And if you told him it wasn't good, he went nuts. That was a problem he had. And so what happened is that there was a thing in him, which is a personality, as he could not cooperate with other people well. And that was the fundamental problem that we tried to solve. I didn't know how to solve it, because I didn't realize he was that way. I could have if I'd known more. But so we lost, effectively, 3 years of productive cooperation. And what happened is, little by little, the NSF began to realize, and all sorts of people began to realize, we're not getting big money yet. We were getting significant money, but not big money. When we're talking hundreds of thousands, not millions, okay? And what happened is we were not producing at the rate that we should have been. That was quite clear to everybody, and certainly to me. And so what happened is that this committee that got formed at the request of Garwin, and Garwin writes to Barden, and he says, he says, I won't go into all of this, it's a letter that he wrote to Garwin. I got from to Marcel Barden. He says, I'm reasonably familiar with the various approaches, that's approaches to gravitational waves. I'm firmly of the view that we do not need right now to spend 40 million or 100 million on such an effort. And if there is such an interest, then I think it would be useful to have a 2-week summer study. That was his proposal. Barden gets this letter in, when it was May, he calls me up, you got to organize a summer study. Well, come on, May, June, what are you talking about? So I said, it'll be a winter study at best, okay? And we had this thing at the Cambridge Academy here. And it was quite a thing. We brought in industry, we brought in all the people who worked on the bars, and brought in a committee that, in the end, Dick Garwin was on it. And this is the report. You can't read it, but I'll tell you what are the important things in it. That committee met for more than a week, and really did a very thorough job of looking at it. The people on the committee, I'll show you the pictures of them, they're right here. There's Andy Sessler, who was the chair of the committee, and Weiss McDaniel. Andy was a high-energy physicist at Berkeley, a machine physicist, and Weiss McDaniel was part of Wilson's empire at Cornell to make the synchrotron work there. And here's Dick Garwin, the guy who was pushing the study. And Garwin was on the committee, but he only had 6 hours to give it. So he trusted these other two guys to actually do it for him. And what did they recommend? It's very interesting what they recommended. The people on the committee, by the way, are right here. I'll read it from my computer. Daniel Debray, who was an engineer at Stanford, Val Fitch, a Nobel Prize winner at Princeton, Dick Garwin, Joanne Hall, who was at Jilla, who was a laser expert and atomic physicist, Weiss McDaniel, the Andy Sessler, Saul Tukolsky, who was the only real relativist on this committee, and then Alvin Tullestrup, who was once a Caltech high-energy guy. And these was a committee, and what they said was sort of unbelievable again. What they said, after they heard everything, and Dick Garwin signed this, by the way, so that he is in agreement with it, was don't screw around, number one. Don't wait, and don't keep making prototypes. Build 2 big ones that are the right size to detect something. That's what their statements are. You're going to see it if you read it. And then, so that was unheard of. Imagine this. I mean, right away, don't build these 4-kilometer things, 2 of them, and don't build them incrementally. Build them as though you were going to build the whole thing at once, which was, to us, just what we wanted. I mean, I was very surprised by that. And then they said one thing. He says, and make those guys who run it, get them the hell out of there. In other words, get the real director. That was their recommendation. And by the way, that was planted by both Kit and by me. That happened. That plant was to get a real director. And I wasn't thinking of myself as a director. That would have been impossible, because then Ron would have left and gone back to Scotland. But no, that was done in the fish restaurant down here, the Noble, Legal Seafood. I remember, never, ever forget it. Okay, so that was the recommendation of that committee. And so what happens, we got this director. And there he is. I hope if I can point out to you. Here's Robbie Vogt, who was once provost of Caltech. And what he did is something, this proposal that was written was a masterpiece, as far as I can see. You can get it on the web if you care. It's a textbook. The first volume is a textbook about the field, which didn't exist at the time. How do you make interferometers work? What's the theory behind them? Why can you improve them by doing these various things? It was very well done. And then there was a beautiful article on sources, which Kip wrote in the first volume. And then the second volume was all about the engineering details. It was well done. And it came in with a price tag around 200 million, much more than the initial study that we did, which was more like 100 million. So, but then there was fancy things in there. Ron demanded more things. That's sort of interesting. Some of the things worked out and some didn't. The idea that you make a mid-station, you make a half-length interferometer. It turns out we fought with him about that a lot. It cost an extra $50 million to do it, but it turns out in the end it didn't really pay off. That's a complicated reason for that. But so in fact, now we gave that interferometer to the Indians, to the people, LIGO India. And we'll talk about that at the end if you care. So anyway, this proposal did one other thing, which was, I think, very smart, and which was to combine the physicists. Here's Ron and Kip and me, and combine them with a bunch of engineers and scientists who were willing to be the engineers. And so that you had the following. You had a scientist who was involved with the guy worrying about the big tube vacuum systems, or a scientist worried about how you design the buildings. And they worked, and then of course all the scientists were working on the interferometers, but there were people who were engineers working on the optics as well. So there was always a scientist assigned to an engineer. And that worked exceedingly well to avoid the problems that you often have in systems where the engineers run amok. And the scientists go amok on their own because they want to spend all the money. But the engineers held them back from that, and you kept the engineers from doing something crazy. So it was a useful combination. And that was Robbie's big contribution, Robbie Vogt's big contribution to this. And then there was beginning of progress. But then things got tough. And here's 3 slides that come from the epic from 1990. This was 1989, that proposal. And you see the time is going on. Each time I give you another date, it's some number of years later. And I'll make it. So the next thing is that then when things got to the point where it was serious, and Robbie began to make the case in Congress, it turns out that we had, and this mistake is partly mine, we began to call this thing LIGO. Now, what's wrong with LIGO? Okay, I'll tell you the O is what's wrong with LIGO, okay? If we had called it LIGE, we probably would have had less trouble. It would have been the Laser Interferometer Gravity Wave Experiment. But damn it, we called it because it was easier to pronounce. Imagine pronouncing LIGE, okay? LIGO had a nice ring to it. And so it turns out O was the Laser Interferometer Gravity Wave Observatory. And that got the hackles of all the astronomers completely up in tears. And some very important astronomers got very annoyed with this. And they were very, very worried that the NSF was going to spend big bucks. They knew how much it was going to cost now. And John Bacall in particular, Tony Tyson, who is a very good physicist, but also had become an astronomer by that time, and Jeremiah Ostreicher, who we always have known has been against this from the beginning. And I always suspected that Ostreicher and Kip had the same girlfriend or something like that. I don't know why they really are at each other. It's just amazing. Watch them. They look like two cocks. They just, so the thing is that the thing is that they went to Congress, and Bacall had just finished a study for the astronomers, and they went to Congress to actually blackball this. And this is Robbie trying to get money, and this is what this article in Science, if you want to look at it, at least you can read that. And that's where that is. In 1991, we began to realize that we had a real problem with the rest of the scientific community, not the physicists so much, but the fact is because we were an observatory and claiming to do astronomy, most of the astronomers saying, these guys can't even detect anything. Why do you give them any money at all? It's wasted money. And that's the way they went to Congress. And they almost won, by the way. It was tough at that time. And so I went to congressmen. Everybody went to their congressmen and started really, telling them what to do. I mean, trying to tell them what to do, or what was good. So there's Robbie trying to sell this thing to Congress. Then in 1993, there was a disaster. That was probably the bottom of the whole thing. And by the way, all through this, the NSF is continuing to support us, continuing to put money into this. And now this one is probably the biggest test for the NSF of all. At the point that was actually kind of critical, what happened is Robbie Vogt and Ron Drever had a falling out, a very serious one. Why? For the same reasons that could now be entirely predicted. Ron, in the design, kept having a better idea, but not necessarily a better idea, but another idea. And if you are already in the business of trying to spend the money that you're getting, and you're talking about big bucks now, prototypes that you're developing. You don't change your plans unless you're absolutely certain that you have to do it. And a better idea has to be demonstrated. And that, if you're going to use it, because what happens is especially if you're now eventually going to go into production, you can't keep changing, because then what happens is then you have the industry just eating you alive. They just love to have you change your mind because they make more money on it. So consequently, that was a prescription for disaster. And I don't think what was done had to be done. I don't think both Ron and Robbie are both complicated individuals. What happened is that Robbie effectively told Ron he was persona non grata in the project and threw him out. And that was just too much for the Caltech faculty. It was too much for some of us also on the outside, but we understood why it happened. It was one of these human things that you could see happening. And so there was no way there was a huge falling out, and what happened is that at that point, the NSF cut off all the money because it looked like no money was being spent. Robbie was running a skunk works. There was not enough people in the thing. Not enough people. The skunk works is a thing where you have the absolute limited number of people, and they barely can keep up with all the problems that you have in the real project. And on top of that, dealing with the NSF on the outside, which is a thing that's continually asking, where did the money get spent? Show us your receipts. Tell us what your schedule is, and so forth and so on. And that's something that got to the point where they no longer could really respond to the NSF properly. And what happened is then, near the end of this period, what happened is both Caltech, and now by this time MIT was very interested in this project. Completely different people were involved at MIT. They were now, the head of the department was a person who understood relatively, cared about it. The provost was somebody who had done laser work. A guy named Chuck Vest had been a holographer. I mean, the president of MIT thought this was a wonderful thing for MIT to be in. Completely different. So I never thought as a kid that administrators would matter at all in anything we do, but they matter tremendously. Okay, just imagine what happened. So MIT was behind it 100%, even more so than Caltech at that time. It's sort of interesting how that transition took place. And then there was a big thing, a big push from all the chief people, the president of Caltech, the president of MIT, the head of the NSF, right from there, and to make it so that they got rid of Robbie, which was unfortunate. And then in comes Barry Barish in 1994. And Barry had been a victim of the SSC closing. And he wasn't looking for a job. He had plenty to do, but he was always interested at Caltech in this field. He thought it was going to be technically a wonderful field to get into. He's actually a guy who loves technology. And he enjoyed the idea, the technology of this. And so he still does. And I think I have a lot of respect for him. And the thing is that, and on top of that, he was a good director. He didn't make enemies. He didn't emotionally react to things that bothered him. He just let it happen. But he was very good in explaining things to people if they didn't get their way. And so consequently, all of a sudden, we had a director who knew how to run a large project. And it made all the difference in the world. Okay, so that's then the beginning of the project. We did a couple of good things in the process, and Barry was part of that. One thing we did, and this is something I'm proud of. What it is called the MREFC line item in the NSF budget. It's a line item that gives the NSF the ability to go and look for large pots of money for a large project occasionally. In other words, up to this time, when we were doing this, NSF did not have large amounts of money. They did one thing crazy back, and it's all forgotten. In the early days of the NSF, because of Johnson, they got into the business of doing underwater drilling. And the reason they got into it is Johnson was not as, well, he's not as crooked as Trump, but he was a little bit crooked too. And what happened is that he wanted to use this new fledgling agency as a way of doing a project that might be interesting to the oil industry in Texas. So you want to drill away into find out if you can get core samples in the ocean? Good, let's get some money for that. It's a huge project. They should have never gone near it. It was the whole Mohole project. And it blew up all their budget completely. And what happened is they never finished it. In other words, it was a project in the very early days of the NSF they should have not gone near. And ever since that project, they were always leery of getting into a big project. So here we are. Now this is 1950. We're now in 1990. That's sort of 50 years later. About 45 years later, we're asking for a big project. NSF isn't used to it, and they are proposal-driven. That's the way they do it. And all of a sudden, we're asking for something which is not a single proposal anymore. It's a whole big deal. And so consequently, we lobby Congress, all of us, to make a line item for the NSF to be able to do big projects. And the very first project, and you can see it in this picture, was finishing a telescope, the Gemini telescope. It's sort of, this is the years, that's the money, and here's a little bit of Gemini. And here's LIGO, big chunk of it goes into LIGO, but then it does other things, a lot of other things, all these other projects. Then there's LIGO again for the upgrade of LIGO, and then all these other projects. So we have suddenly, by doing this, once Congress says, let's have a line item, that stays in the budget. It doesn't go away again. That's interesting. You can always change the number in the line item, but you don't get rid of a line item without a big deal. So we then did something useful for science. And what happened is most of the astronomers don't realize this. Now they are with us because we've done some science, but the fact is we already had done something for them also by getting this thing through, and I want credit for that. Okay. So here are the people that Barry brought on that made it no longer a skunk works, and he brought on a really first-class project manager. He got a project engineer and a deputy director, and we started forming a real project. Here are people who then became he'd started something called the LIGO Scientific Collaboration, which Robbie Vogt couldn't start because he didn't like the idea of having a whole other group of people he had to deal with now. But what the NSF was insisting on, we'll get to that in a minute, was to make an ancillary organization that was a LIGO collaboration, which now, by the way, has grown to something like 70, 80 different entities with about 1,000 people. And they published that great big paper that you saw. So it turns out that that was something that Barry pushed through, and with the help of a lot of the people at the NSF, again, driven by Isaacson. And these are people now within the project. I think I'm running out of time, so I better not go on. I just want to show you. Here's the LSC. And that's, you can see it's a huge group of people, and these are all their different their emblems. And this works pretty well as far as the collaboration goes. I was involved with smaller collaborations. It seems to be working reasonably well. And so, okay. Now, I think I have here one last thing about the NSF. And that is, these are people who actually were critical in this whole process, who were directors of the NSF. Eric Bloch was the first to actually try to get LIGO going. And the way he did it is by making he did something not so good. He got all the radio astronomers mad as hell at us. That's what he did. Because when, I don't know how many of you know, there was a big antenna that fell down in West Virginia. You might know well, probably, because you probably used it, right? And that antenna collapsed on a Christmas day. And Eric thought that, wow, well, the head of the Appropriations Committee, Robert Byrd, it was in his state. So he figured he could sell Byrd any old antenna. Why not a gravity antenna? It made no difference. And so, okay, but the radio astronomers knew the difference between a radio antenna and a gravity wave antenna, and they were having none of it, okay? So that was the beginning of a major other problem we had. Again, they stuck with us through it, even though they made what I would call a strategic blunder. Walter Massey was the head of the NSF at the time, at the height of the time when the astronomers were going to give us hell on Capitol Hill. And they came to him. John Bacall came to him and says, we think you are out of your mind supporting this LIGO thing. It's never going to work. And Walter said, I'm the director of this thing. He did. I know I'm paraphrasing. I don't know how he did it. We think it's just the right thing for the agency to do. It's sort of impressive against this guy, against a very important member of the National Academy saying he shouldn't be doing this. And then lastly, here's Neil Lane, who was the guy who helped push through the MREFC thing, that new line item. So these were heroes in this business. And then here are more heroes. These are people who then were in the LIGO business. Here's Rich is not in this picture because we have him already. But then Bev Berger, many of you who are in gravity know her. This is the guy who's now head of it. I'm not going to say much about that. And then there were people. Here's Bob Eisenstein, who was the father of one of your professors. And then Harris. These were people who were head of the other assistant directors of the NSF, absolutely critical for LIGO. And then these were the people who actually were the people at the NSF who worried about LIGO daily. There's always a person who's a manager at the university. A manager at the NSF. And okay, if you want, I will tell you about some things that we've accomplished, but I'd rather not. I'm past the time I'm allowed to talk, I think. So who would like to hear a few things about what we've discovered? Oh my God, so, all right, this won't take that long, but it'll take 5 minutes more. I'm just worried about keeping you because you've heard the story that I was going to give, but I felt you ought to know what the end point was. So, okay, so the end point is we know that we have these are two detectors. There's one in Louisiana, and there's one in Washington State, that's the basis. But there are more detectors. There's one in Italy called Virgo. There's a smaller one in Hannover, Germany, which is a research detector. And there are two new ones in the process of being built. One in Japan, inside of a mountain, and then another one which is using that half-length detector in LIGO in India. It'll be a full-length detector when it's built in LIGO India. And the reason for having more detectors is mostly to be able to couple better the gravitational wave sky to the electromagnetic sky. The only thing you can do with the two detectors, as you'll see in a minute, when you have a detection, you see something first in one. Let's say the thing we saw first, the black holes. We saw it first in Louisiana. 7 milliseconds later, let me in fact go to that. That's this. These are the waveforms we saw. This is the one in Washington State. This is time this way. That's strain that way. Here's the one in Louisiana. And you can see there's noise here, but there's something coherent, and it's about the same thing. You can superpose these things, but in here, this was the very first detection. And one of those waveforms was 7 milliseconds in front of the other. And that was because the source came from the south. It hit Louisiana first, went through the Earth, then came to Hanford and came after that. And you have to slide those two pictures to get them on top of each other. And the spectrum is sort of down here. That's the time series. That's a theoretical thing with the same filter. That has a filter. By the way, that was such a powerful source that the only filter you needed was the same thing that you have on our radio, a tone control, a bass control, and a treble control. That's all. No match filtering, no nothing. You could see this directly in the output of the two. I mean, this was one of the biggest sources you could ever see. And so, and here then is the Fourier transform of this in a way. This is time, and this is frequency, and it ran from about the low end of the piano, got really strong at about middle C. That's this thing. And that was two black holes that weighed about 30 solar masses each, and they made a new black hole. And here are all the black holes we've now seen. Those are just, that's a little pretty picture. You can see what's going on here. The black holes that as a radio infrared X-ray astronomers had seen. And they know these are all, this is mass, and this is just no axis at all, just showing them all. But here, this is the one, the first one, and the second one, the third one, the fourth one, the fifth one. The fifth one, by the way, was also seen by Virgo. That was the first time. And it made the error circle for knowing where it is much, much better. And it proves the thing we're trying to get at. Namely, the more detectors you have, the better we can couple and make the area on the sky smaller so that we can actually, I mean, when you tell an astronomer, go look at 1,000 square degrees, which is what you can get from two detectors, they laugh at you. I mean, most telescopes, slew 1,000 degrees, you're out of your mind. And so, but when you get down to, with 3 detectors, it's down to 30 degrees. That's still pretty awful. And when you get all those detectors that I showed you together, you'll get down to about half a degree, the size of a moon. Okay, something like that. So then the next thing, and this is sort of the last slide, is the big event that took place almost immediately after where Virgo saw the black hole. This is the neutron star collision. And what's different about it is you can see it best. You don't, this up here is, this is what was seen, or one way. This is again the frequency. This is time, frequency, and here is a very long chirp. You can see it. That's it. And it was seen in both detectors. It was not seen in Virgo. But the reason Virgo was very important, it turned out it was not seen at Virgo. It should have been seen in Virgo. But the fact that, the very fact that it was not seen in Virgo told us where it was. It was in the null of the pattern, the antenna pattern of that particular detector. That just happens to be unlucky. They didn't see it, and they helped enormously in determining where it is by doing that. And so what happened is that that source was seen by the Fermi satellite, and it's 2 seconds or 1.7 seconds after a gamma ray burst was seen after this. And then there's another instrument on Fermi, and then there's another satellite that also saw something, not so convincingly. And so this was the first time that, first of all, we'd seen a neutron star collision. We established that a neutron star collision makes gamma ray bursts of the short kind, which is something we guessed at. People had written about, Zvi Perron had written about, Schramm had written about, but that was still a theory. And now here all of a sudden was real proof of it. And I don't think I have all the story here because I was going to protect you from what, this is the last slide I'll get to in a second. But that then led to a lot of science because it was seen within about 8 hours by virtually 300 other astronomers. And they then watched the thing. In fact, you had a very big group here at the CFA that saw this Ido Berger. Yeah. Berger did a very careful study of this, but others have too. And it seems to show that they were seeing what is going on here when these two neutron stars collide is you are seeing the R process, the process of making the heaviest elements. Because, you know, I don't know if you know, but you don't make the heavy elements in the supernova. You make, there's always been a question, where were they really made? It turned out when you do the numbers for this, it's close to explaining it. The reason why I say close to, what I'm disappointed by, is that there were no lines seen. What was seen was an opacity. And the thing that I wished there had been some iron lines, there had been some gold lines and uranium lines, but that was, the system is just too activated. Just the Doppler shifts are just too large. The Doppler widths are huge. So you don't see lines, but maybe if it cools down, you'll begin to see them. Anyway, that would be nice proof that you're really making the heavies in there. But so far, this is based on an idea of Metzger's doing the opacity measurements, and it's based on measurements that were made also in Los Alamos. So last thing I just want to say, what this picture is just a picture of where this field is heading. And there's much more than it than just LIGO. So this is frequency, and this is strain, but this time it's strain and amplitude. And here is LIGO at high frequency, sort of 10 hertz to 10 to the 4 hertz. It's measuring compact binaries. This project is LISA. It's a triangle of satellites going around the sun behind the Earth. It's in solar orbit around the Earth. And that has a chance of seeing big black holes, small black holes falling into big black holes, even the radiation of binary systems in our own galaxy. And that is as old as LIGO, that project. That came out of that committee in 1974. Okay, and then that will hopefully now fly. The Americans bugged out of it in 2011 because they were having trouble with money. And it was not Trump. It was already trouble with money before then. And what happened is that James Webb had caused them some trouble, and this is what caused this to be dropped. Well, the Europeans kept it going, and they're now in charge of it, which is sort of a pattern I don't like, but that's the way it is. Even though I come from Europe, we've done that with high-energy physics. I don't like the whole... What? Say what? They did a beautiful experiment, and I didn't show this here, but I could. That's another colloquium for another day. Okay, they show that the technology and the interferometry seems to work. The other one is using pulsars as all over the galaxy, and that's going on. It's a timing experiment. I think the CFA is part of this. You look at pulsars everywhere in the galaxy, and especially millisecond pulsars. And if a gravitational wave comes through the galaxy, it'll cause the following kind of pattern. It might make all the pulsars in the north and all the pulsars in the south to slow down a little bit, and all the ones in east and west to go faster a little bit. You look for that pattern. And that then is an indication that you've had a gravitational wave come through. Maybe it'll be from gigantic black holes, 10 to the 10 solar mass black holes. But you've seen them in the Hubble pictures. So that is an experiment that's ongoing right now. And lastly, an experiment you know all about here, because this is all you. You guys have the B-mode experiment here, and so do other people. That, I hope, that's the polarization of the cosmic background. I hope that works, because that's the most spectacular of all the experiments I think that you can do. To look at the primeval gravitational wave background. Due to the density fluctuations, those gravitational waves induce in the plasma. And that's a spectacular experiment. I hope it works. Thank you.
Thank you very much.
Yeah, you're quite welcome. I probably used every minute that anybody has time for.
Oh, well, everyone has just been, really enjoyed the lecture, and I loved hearing the whole story. So we have just a few minutes for questions, so please raise your hand, and we have a mic.
You do have a mic, good.
Recording session.
Okay. There was a bar that was being built in Italy that was being cooled to several millikelvin. And what happened to that? And what is the future for bar gravitational detectors?
Well, I'll tell you right now, I don't think it has a future. And it has nothing to do with, I'll tell you, it's so easy to show. Remember that what you're looking at is a strain. That's what's being seen, okay? And a bar is coupled acoustically. So the length of the system that you can make, if you're looking for something that is going to be resonant or response at the frequencies we're talking about here, let's say up to 5 to 4 kilohertz, you're talking about something that's limited by the size that's determined by the velocity of sound. So if you want to make a measurement there, you have to make a measurement for delta L over L being the same. You have to make a measurement that's very much smaller on a bar than you do on a thing that can be made optimally long with a velocity of light coupling the two parts. In other words, an antenna made of, a gravitational wave antenna made with light will be 100,000 times more sensitive, just from starters, than a bar. Just from that difference in the velocity of sound to the velocity of light. So I don't think it's worth it, okay? And you can make interferometers, by the way, that are resonant, if that's what you want. It's not hard to do, and I gladly will tell you about it when not for everybody. It's a way of making an interferometer be a resonant system too. It's not the resonance that's important. So I think bars are over. It's not that I'll tell you why I'm thinking about it so much. And this is important for people in the room who do neutron star physics. It looks like now most of the models of neutron stars now, the ones like the thing that collided, that we saw the collision of, will have an epoch at the very end of their cycle where they collide, and then the new object that forms before the black hole forms has normal modes of its own, which have fairly high Q normal modes. For example, it depends on the equation of state of the nuclear matter. And what happens is that you will get resonant, depending on the equation of state. If it's a soft equation of state, you'll go down to about 1 kilohertz. If it's a very rigid equation of state, it'll go up to about 3 kilohertz. Somewhere in there, there will be lines. You will be doing spectroscopy of the nuclear medium, which is sort of spectacular. And those things were suddenly reasons to do bars again, I thought, because you could resonate them. And it turns out I just did the numbers again for myself. I can beat a bar by a factor, easily a factor of 10 to the 4, by making a resonant detector, if I want to do it that way, resonant interferometer system. So I don't think bars will come back. The only bar system that has approached having some sensitivity you would think about are spherical bars. I'll tell you, I thought you were going to say the people in Brazil. They've been thinking about this. And there's a group people in Brazil particularly. A spherical bar can have, you can have it omnidirectional, and you can add, you don't have to worry about having it oriented properly. But I think it doesn't change the argument that I made. It's still stuck with the fact that it has a finite size that's determined by the velocity of sound and not the velocity of light.
Right, yes.
Obviously,
where are you? Just raise your hand so I can see where you are. Okay. Yeah.
there are different sources, as you've made clear, for the gravitational waves, including possibly things associated with the very early universe.
Right.
And are there any kinds of detectors that would be used for looking at some of those that you may not have mentioned already in your talk?
No, I know what you're asking. I mean, for example, that's why I think the B-mode experiment is so interesting. And by the way, if the B-modes succeed, I think it'll be interesting to build what I'm about to tell you. The only plan that I've seen which even approaches being able to detect the primeval gravitational wave background. I'm not talking about, there will be a foreground in gravitational waves, much like it is in the CMB. I mean, all these black holes we're seeing and all these neutron stars, they're going to make a foreground noise, which you have to calculate or be able to look into. But if you really want to look at that very broad spectrum that was generated by the inflationary period, if it's true that there's an inflation, and that's what we'll learn from the B-mode experiment, then it turns out that you can't do LISA. LISA will not do it. I'll tell you why. The number that people are predicting for a reasonable model is that you have a gravitational wave power density, energy density, that comes from that early epoch, which is around, it's pretty flat, and the region where we could make instruments, at about 10 to the minus 15, 10 to the minus 14 of closure density of the universe. That's the way people like to present it, in terms of how much gravitational wave energy density is associated with a number that's cosmological. In this case, closure density is 10 to the minus 29 grams per centimeter cube, okay? So that gives you then, and if you use that formula, which I pointed to, that pointing theorem formula, you can get the H values. They're tiny. And it turns out LIGO can't do that, and LISA can't do that. And it turns out that there is an idea that could do it. It's called Big Bang Observer. And that's taking LIGO technology and putting it into space. And there you can just about do it. But I don't think that's going to happen until the 2050s. In other words, I'll tell you what's the difference. LISA's technology is heterodyne interferometry. LISA has millions of kilometers baselines, and it has position sensitivity that's only about 10 to the minus 12 meters per root hertz. LIGO has 4 kilometers, but position sensitivity of 10 to the minus 18 meters per root hertz. So there's a factor of 1,000,000 in the sensitivity of position sensitivity. And now, the strain that's being measured in LISA is still around 10 to the minus 20 or so. It's a little bigger than what's measured in the ground-based thing. So it turns out if you want to do that 10 to the minus 15 of closure density, you've got to take, or 14 of closure density, you've got to take LIGO technology, which is very different than LISA technology, and put it into space. And nobody has the courage yet to think that through. It's a very different experiment. Okay, you have to have cavities and fringes that are held with servos. Heterodyne spectroscopy is very forgiving, but it's not as sensitive. So yes, there's an idea to do it, but it's not something that we're going to do right away. Okay.
Okay, I think we'll just take one last question.
I believe you said at the outset that NSF couldn't do something like LIGO today, and yet LIGO's this wonderful success. So why is that?
Okay, I'll tell you why. I'm glad you asked that question. It's a nice way to end the thing. What it is it has to do with the way the proposal review system works. In other words, there's two things that are new about LIGO. One of them is that it suddenly has made, and they have to come to terms with this, the NSF. NSF has become a mission agency by accident. See, NASA is an agency that doesn't support all of science, but it supports things that are in its mission. NSF has always supported those things that it gets proposal pressure on. That's the way they don't have an internal idea, we should support this and this and this. Now they're beginning to do that. You notice that in the line item that they now put out as something that they look forward to, and they're asking really for proposals in this. They have some ideas that they want to support proposals. One of them is called multi-messenger astronomy. And that's a code word for, yes, gamma ray astronomy and infrared gamma ray, gravitational wave astronomy. That's the first time I've ever seen them really do that. There is an organized mission that they would like to support. That's not been their thing up to now. I mean, and because of the MREFC thing, now they suddenly have many, many large projects, and they have to change the way they think. That's one problem. But now, if you have yourself ever applied to the NSF, you'll find out that virtually every proposal you get, I mean, I've been on committees, and you find that it happens. They always ask, what's new and original about this thing? What is groundbreaking? And then how much of it is ready to go? Okay, and so consequently, things as speculative as what this was, it just doesn't have a chance. It's the proposal review process. So my solution to that is to say to Congress, look, why don't you make sure that the NSF puts 10%, that's maybe too much, 5%, that's a huge organization now, into things that are very speculative. That would be one nice thing to do. And that's the thing we could push for. Yeah.
Okay, well, I have a couple of announcements. So first of all, I'd like to thank Yolanda Davis, who really helped put this event together. And then I want to remind you that there's a reception upstairs on the 4th floor in Jefferson 450 with the desserts and drinks. And finally, of course, thank you again to Professor Weiss for a wonderful lecture. And